Okay. Well, this is the pointer.
No, this is not a pointer. That's a remote. Use the
And the laser.
laser. Okay, so last but not least, the last speaker of the program is Krzysztof Kutak. Please.
So thank you for invitation to participate in this workshop. So I changed slightly a title. So the idea is of my research is to kind of generalize the low-X evolution equations. And this research is based on these papers. So in high energy factorization, we can calculate now, I mean, automatically all three-level amplitudes for any standard model process, and this is achieved within newly written Monte Carlo program. So it was a kind of a huge advancement, in my opinion. So and this method to calculate these amplitudes was based on helicity method, and it's consistent with the Lipatov high energy approach, high energy effective action approach. So within this Lipatov high energy effective approach, you can calculate some, but the problem is that in Lipatov effective action approach, you can calculate processes with rather small multiplicity. So one definitely needed some other methods to calculate any process. So this is advancement concerning the hard parts. But in my opinion, there is still an open problem of evolution in high energy factorization or CGC. So here I kind of collected a list of, yeah.
So here you're saying energy factorization or CGC. Do you?
I mean, okay, this is a bit. It's not exact. I mean, this is a rough statement, but I mean that it's high energy physics. I mean, and then one can be related to the other in some linear regime or something like that.
So they are not exactly the same.
No.
But you consider the CGC as being a model of high energy factorization, or?
I consider CGC to be more general framework. More general, because they account for non-linearity. Yeah. But by this, by high energy, by what I mean is that within high energy factorization, you have, but in CGC, people don't address, for instance, hard matrix elements, I mean, of high multiplicity, etc. That's why I just kind of roughly combine these two things. But what I'm after here in this slide is just the list of available frameworks or which can give you a Parton density function, or in particular gluon density function. So within you can get gluon density function solving PFK, BK, or GMOC, but in principle this is just limited to gluons. So in principle, it's very imprecise. One can get quarks, that was mentioned yesterday in Fang's talk, by getting gluon and then convolving something to get quarks. But still, in the evolution, you don't have they don't talk to each other. So that's a problem. Then you have a CCFM. The problem with CCFM is that in principle it jumps from low Z to large Z, and doesn't account for quarks. And this has been seen presented by Hannes Jung, who was showing that CCFM has difficulties describing processes where there is a contribution from quarks. Then there is a formalism by Jan Balitsky and Andrei Tarasov, So here, the thing is that there are, at least at present, they don't address quarks, but they have non-linearity. And the interesting thing, as I realized recently from discussions with Jan, is that the kinematics of the basic vertex is the same as in our approach. But the kernel, to see this explicitly, one need to do some work to really show the equivalence. So then there is a formalism by Kimber, Martin, Riskin, and Parton branching. So roughly, both of them are based on, you start with collinear factorization, you get the collinear PDFs, and then in this Kimber, Martin, Riskin approach, you apply Sudakov form factor, and then you, and then you get a kind of PDF, which depends on hard scale, transversal momentum, and X. But in principle, to use this within this, together with hard matrix elements in the high energy factorization approach, one would need to refit the whole distribution, because originally it is just collinear distribution fitted to some with collinear hard factors. But this procedure gives you kind of transversal momentum dependent PDFs, but they are not completely constrained. The Parton branching method is with these aspects is on the same footing. Then there is a formalism by Catani, Cefalani, Stashte, and Salam. So this is kind of an ansatz for coupled system and matrix equation. But the problem is it's kind of a model, and the quark splitting functions are KT independent. So here are just a few slides since I promised to say something about this Parton branching. So and in general of the cascade in KT program. KT is the matrix element generator. So here is the correlation of delta phi distribution between the two jets, and we applied this KMR PDFs together with Parton showers, final state Parton showers, initial state Parton showers, and KMR Parton densities. So for this PT range, we have kind of reasonable descriptional data, but then when we lower the PTs, we depart from the data. So at present, we don't completely understand this, why this happens, but the thing is that we are just using the procedure we just described before. We just take the collinear PDFs, so to say, multiplied it by Sudakov, and calculate the cross-section. To be fully consistent, we should at least refit the new PDFs with some inclusive data like F2 to constrain better the initial the parameters.
The data are from,
Excuse me?
the data are from.
This is from Atlas, I guess.
So we did a sort of the summation for this, actually a pretty good description of the data for the digest.
Okay. But did you account also for some showering effects?
I mean, that's shower with sort of.
But final state shower.
What do you mean by that?
Radiations from produced jets.
Yeah, we have that.
And did you constrain the parameters of Sudakov to some other data, or you just took Sudakov and multiplied by distribution?
Okay, so the conclusion that, I mean, I can go on for whatever. So the conclusion is for so because you have hard process, you digest, right? You wear so knowledge. The dominant constraint is particularly part of Sudakov. So non-free part actually doesn't contribute significantly to this envelope. So you can multiply factor 2, you get the same answer.
But you see, here I also get quite a good description of data, but here don't. I mean, so I'm sure that the correct procedure is to fully constrain all the kind of elements. And that's why I'm presenting them. I'm not presenting this to hear myself, but just to,
okay.
to show that.
Pseudo-couplet summation is not just quantum distribution itself, because we have digest, so you have all the soft ground radiation associated with J as well. So I can give you reference. It's very complicated summation formula, but the conclusion that we get very good description for LHC data and also telephone data.
But it depends again. What formalism are you using? Because here it's
No, I mean,
CCFM.
no,
So like of this part of the.
No, we are just using pseudo-code. Just based on TMD summation. That's it.
Okay, but what I'm saying is that here in CCFM, Sudoku is part of the distribution. So it depends on the. So in the thing that you are talking about, probably it's something outside of the distribution, right? It's not the part of the PDF.
It's both, right? I mean, there's part of the PDF and part of the
yeah.
Okay.
So yeah, it's a TMD summation.
I see. Okay.
Just apply to the digest case. What Christian also talking about this morning is maybe it's vibration breaking effect, but what we found actually for this observable actually seems to work.
Okay.
Yeah.
Good. Okay, so here is another example. So this is example of Peaky distribution of Z plus jet. So here again, I mean, here actually this Parton branching PDFs were used, and we see that when we compare the results with the PDFs from Parton branching and with this cascade Monte Carlo, we are doing kind of well in this region, but here we differ from the Pauhek result. It doesn't work. I lost this. Okay, so it's very, very weak. So then there is this comparison to Pauhek results, which is okay. So what is interesting here is that when we switch off the multi-photonic interactions from Pauhek, the Pauhek and cascade gives are consistent in this region where they differed a lot on the previous slide. So it is this will be just
I can swap this too.
Yes, it works. It works. Thank you. So this also points at some additional effects like this MPI effects, which are relevant in low PT regime. So usually this is not addressed within standard factorization. Okay, here are some delta phi distributions. So the goal is, in principle, I already mentioned this, but to go beyond DGLAB and BFKL by generalizing splitting kernel, to have coverage of all Z regions, so not like CCFM, for instance, to jump from low to large, but to have also the moderate Z values, and to reproduce both limits in appropriate regions, and to implement in the end all this into a Monte Carlo. So within the method that I'm going to use, we will not be able to address the nonlinearities. So this is the limitation. But here the saturation is not our primary goal. So the methods, the tool which we will use, which I'm going to overview now, is this very old already, but still useful, Kurci-Furmański-Petrancja method. So within this approach, one just considers some cross-section and performs the ladder expansion. So it means that one decomposes this cross-section in terms of hard matrix elements and then some kernels, which then after resummation can be linked to roughly speaking, to a PDF. So technically, what it means, we have this cross section here, this expression, and then one just introduces some projector in all this kind of lines to separate the most singular contribution. And then there are kind of, in the end, this can be shown to kind of boil down to projectors, like projector which picks the pole part, and projectors which perform some spin average. And in the end, this thing can be decomposed as a convolution just in X, where we have the hard matrix element and something which then in the end become proportional to green function or PDF. Okay, so here is the kind of we are using this as a kind of a tool. So in principle, the thing is just to in the whole formalism to isolate the part of the formalism which allows you to calculate the splitting function. So here is just the standard. You just draw standard Feynman diagrams, and then introduce appropriate projectors, and then in the end you get the splitting function, which is just this one. So so this method was used and generalized by Catani and Hauptmann to obtain a KT-dependent splitting function. And then what they did is that in the standard CFP method, what you do, you just assume that this incoming parton has only this longitudinal component, while and its own shell, while the other one, the outgoing, has all the components and it's virtual. So what Catani and Hauptmann did, they just added here this KT, and then in the end they were able. I mean, this is what they got, and the thing is that they had to generalize the projector for incoming parton, and it has after their observation, and they obtained this projector. So what was the starting point? Actually, was just a process for gluon going to quark anti-quark. So and this final state was massive. So they just started with this kind of nonsense polarization, as called by Gribov, and then they processed this formula and were able to kind of obtain this. But there was one assumption that they had to do. I mean, the final state, there were just massive quarks. So then this matrix element had some gauge invariant properties which are not there anymore for, let's say, if you consider purely gluonic channel. However, they obtained this splitting function. So we realized later on that in order to obtain the correct results for gluons, I mean correct is that, okay, so we started in our calculations also with this projector, but then we were not able to obtain correct BFK limit. So the thing is that we had to undo this procedure. So the correct projector is actually this one. So the thing is that if you want to calculate such splitting function, the important thing is to remember that one has to also generalize the individual vertices. So the vertex, which has to be here, comes either from this Lipatov effective action, but one can also derive it using this helicity methods. But the method doesn't matter. But in principle, the thing is that if you have to add all these three diagrams and then rewrite your amplitude as an effective vertex, which has information about this kind of induced terms, and it has information about the fact that the incoming gluons are not on mass shell. So in the end, one following this procedure for all the quarks and gluons channels, you get such projectors and such vertices, generalized vertices. So this then can be used just using this Furtchi-Furmansky-Petranci formula and plugging just appropriate expression for this KGG, for instance, or other channels, and then appropriate projectors. And then in the end, one gets, for instance, this PGG splitting function or the others. So here I'm just focusing on the real emission parts. So virtual are still to be addressed in the future. But this is the collection of all the splitting functions, and I'm presenting here for simplicity just angular average. So now the limits. So this is just a standard DGLAB PGG splitting function obtained in the collinear limit. It is just the KT is set to 0. This is the BF limit, so Z goes to 0. And here, what you notice is the singularity in which appears when Q is equal to K. This is the real part of the Lipatov kernel.
So in the DGLAB limit, you need the endpoint contributions, right?
Yes. But this is, as I said, I mean, this will be we will address this in the future. The virtual part.
Yeah. Okay.
But what was surprising, we didn't kind of intend to get this, but we just obtained this, and we got the CCFM splitting function. I mean the real emission part of CCFM in the angular ordered region. So before this, I actually thought that CCFM is kind of a model. Just you take a piece of leading. I mean, it looked like a model. But here it seems that if one has a general enough kinematics and takes the appropriate limit, one gets it from the splitting function. So yeah, here it is just this limits indicate just we don't know at present the virtual pieces. That's why I had to introduce these cuts. But eventually, all this will be fixed by appropriate limits on the phase space. Yeah, okay, so what was also puzzling here is that at this order of perturbation theory, we cannot, it seems that we cannot get from diagrams, we cannot get virtual pieces to regulate this singularity where Q equals to K, and it is present in all the splitting functions. I mean, diagonal and non-diagonal. And in particular, the problem and the problem is seen, for instance, with this PGQ splitting functions, because I cannot draw the diagram which would regulate virtual diagram which would regulate the singularity. But then the observation was the following: that in kind of matrix evolution equation, one should get the contribution to gluons from quarks. So the idea was to just couple them, just and to study, to have some such a model, just to see what happens. I mean, and the idea is that virtual contributions from gluons will regulate this divergence coming from, which is present in this splitting function. And the observation, actually it works, but one has to realize the following thing. So BFKL equation is usually can be written like this, but this is not the kind of usually presented form of this equation, but it's useful. The thing is that then, using this form, one can eventually rewrite the BFKL equation as a Regge form factor acting on real emission part. So this Regge form factor, it gets a contribution from unresolved real emissions and virtual emissions. And it depends on some cutoff here. And the cutoff is also present here. So in the end, one can numerically demonstrate that that the solution of this equation is exactly the same as solution under some BFKL equation, provided one goes with this cutoff to very small values. So this idea is used then to perform a resummation on this coupled system. It is the BFKL plus the part coming from the quark contribution. And indeed, in the end, after this resummation, one gets such equation. And here, this plots just show what happens if you go to lower and lower values of mu. So this blue squares just shows the contribution of the full quark term, and here let's say just the low z limit of this quark term and finite part. So in general, the statement is that if we just focus on the blue, we just see that the lower mu is, the more flat the line is. So it just doesn't diverge. So this divergence is regulated. The divergence of quarks is regulated by gluons. So here are my conclusions and outlook. So we obtained basically the splitting functions for the quarks and gluons, and in the end, we want to still obtain the virtual contributions to write the appropriate system of evolution equations and to eventually to implement to Monte Carlo. So here, I also would like to kind of advertise this workshop, which will be in Krakow in something like 1 month. So I assume that it's a bit too late for interested people to register and to participate, but at least it will be online. So if someone is interested in having a look at some slides, just please do this. And this is also advertising the series of these workshops, because next year we will definitely have one somewhere. So yeah, thank you very much.
So, questions?
So can you back to your evolution equation? Yeah. So you have quark goes to gluon.
Yes.
Do you have ground boost clock?
No, this is just one piece. I mean, I just wanted to see what happens when I introduce this screening thing, because I still I want to have as a next step the full system.
Okay.
So here it is just to demonstrate that this Sudakov regulates this divergence.
But when you do the numeric result in your next slide, what do you choose for the clock?
I mean, okay. So I have I took some distributions obtained, let's say, from the Kimber-Martin Risking framework. I plug it in here and perform the iteration of the kernel.
One iteration.
Exactly.
Okay. I mean, then you should have coupled them together, right? So clock
of course, sure.
Other questions? Maybe I have some curiosity because still I don't understand. I have to admit that I didn't look very deep into the Martin Riskin papers, but still I don't understand the point of starting from a collinear PDF and generating the transfer momentum dependent one.
Mm-hmm.
And how is it different from simply doing KT reservation? Is it the same thing, or is it a bit different?
Okay, so what they do, they
the audience here, maybe they're now.
So what they do, they just rewrite the Diglab evolution, and then they just observe that the cutoff that they have there is some mismatch between virtual and real emissions, and then they are let this cutoff depend on the transversal momentum, and this is the kind of the idea to generate KT dependence on top of hard scale. But I mean, this is while I use this. Okay, I'm not saying that it has a solid kind of fundaments, I would say, but before this pattern branching method was introduced, I mean, this was a kind of a formalism which allowed you to have this KT dependent distribution, and it's not based also. It's very different than this Collins-Soper-Sterman thing, but okay, people are not using it anymore. Yeah.
Any other questions?
Or maybe a comment. So recently, Yuri Kovchkov and Matt, they are studying also looking for small acceleration in quarks in the context of spin-dependent distribution.
Yes.
For example, helicity distribution, tensority distribution.
Yes.
So maybe some of the techniques that's actually also refer to this are. I mean, at that level, at the polarized part distribution, polarized ground distribution, you have to basically take into account everything. So I mean, they are in the same order as noise. I mean, here because unpolarized ground distribution, of course, the BFK always take over small x. And it's in the context in the framework of BFK, you can forget about the clock for the moment, right? But for the helicity, they have to take into clock contribution.
Yes, but you know, the thing is that I would like to have still large Z. I mean,
I see your point. Okay, I got it. Yeah, they are of course still limited in the small x.
Any other questions to Krzysztof? If not, let's thank him again. Okay, so now we have still some time for discussion. So